Thanks for coming. I'm going to talk about, this is largely going to be expository stuff I've known for like 20 years. It's but kind of a change in perspective of what I think is really fundamental. And I may go out on a limb and make a conjecture about something at the end. I can't decide whether I want to conjecture it or not. Anyway, when I was preparing the talk, as Marcus knows, when I was preparing the talk, once again, I had this horrible feeling of, I'm going to start with basic stuff, do all the background, and then by the time I get to kind of the example I want to do, time will be up and I won't actually get to do it. So I decided I'd quickly say Milnor Number stuff, and then just do the calculation that I want to do at the end without telling you what it is I'm calculating, and then spend the rest of the time explaining what I've just calculated. So, I think you guys know this, but I'll start in 1968 with Milner. I'm going to leave out lots and lots of things, why Milner was interested in this, exactly how Milner dealt with it, I'm going to let U be an open neighborhood of the origin in Cn plus 1. So the origin is in here. And let F be a complex analytic function that takes the origin to 0. So analytic. Everything will be complex analytic, so I'll just say analytic. So saying that the origin goes to 0 is another way of saying that the origin is in the vanishing locus of F, the set of points that maps to 0. I also assume something that I'm so used to assuming that it actually makes me write bad things sometimes. Close enough, if you take U close enough to 0, then I'll assume then this is true, and I'll assume that U is small enough so that the critical locus of F inside of U, which is the only place we're looking, is contained inside the hypersurface defined by F. So that happens if U is close enough. The critical values of F are isolated, or locally isolated. So, and this is, Milner actually dealt with polynomials, so he didn't have a U, he had all of affine space. In fact, I never write down examples that aren't polynomials. You just go ahead and do the complex analytic version because you can, and it gives you a little more freedom to work in analytic, the ring of analytic, the ring of convergent power series. So what did Milner do? He looked at this is not how he defined the fibration that's now known as the Milnor Vibration, but he proves that this is equivalent partway through his book. He really doesn't use this much at all. So you look at this map, where this is a small open ball centered at the origin. So epsilon is small. How small? Sufficiently small. And delta is small compared to epsilon. And both are greater than 0. And if you look at this, what Milner shows is this is a locally trivial vibration. Over a circle. Oh, maybe, yeah, this is a complex disk, so its boundary is a circle. It's a locally trivial vibration over a circle. This is now called the Milnor Vibration. And it's fiber up to various things, depending on what you care about. The fiber equals the Milnor fiber of F at the origin. So. Great. This vibration compactifies nicely. You can just take away the open ball, make it the closed ball. And then the Milnor Fiber is now a compact manifold with boundary. Oh, dimensions. I should say what the dimensions are. So F inverse would be a hypersurface inside of Cn plus 1, or actually inside of U. So it is complex n-dimensional. So this is complex n-dimensional manifold. If you compactify it just by taking the closed ball, then suddenly, well, it can't be complex anymore because the fiber has boundary, but the interior is a complex manifold. But now this is a 2n dimensional compact. So that's real dimensions, compact manifold with boundary. And the big deal, or one of the big deals, that Milnor cares about the most, if you let S be the dimension of the critical locus at the origin, S, I'm thinking singular, that's why I always denote it with an S. Of course, it's the critical locus, not the singular set. There's a distinction there. Anyway. So let S be that. The case that Milnor deals with in the most detail is Milnor deals with the case where S is 0. So where you have an isolated critical point. And then what Milnor proves is that in this case, the Milnor fiber has the homotopy type. So this is homotopy equivalent. Of a wedge of n spheres. A wedge, this is the one-point union. Of a finite number of n spheres. So a one-point union, it just means a bunch of spheres attached to each other at a single point. Yeah, that's going to be. It's frequently referred to as a bouquet of spheres. And that mu is now called, depending on what you want to emphasize, the point or the function. Some people would write mu sub 0 of f. Some people would write mu sub f of 0 if you're going to start moving the point around. This is the Milner number of the isolated critical point. And it completely describes the homotopy type of the Milnor fiber. So topologically, that's why it's important. Of course, I haven't told you why the Milnor fiber is so topologically important, and I'm not planning to. I could talk about that for hours. But big deal, other big deals about the Milnor number. Well, one of the big deals is that it can be calculated algebraically. I mean, in my mind, the reason to work in the analytic category or the algebraic category is so that you actually have a prayer of calculating something algebraically. What Milnor proves is that this Milnor number is the degree of the gradient map. I'll put an epsilon here so it looks like it goes to and from the same epsilon sphere. If you take the gradient of f, it is, since f has an isolated critical point at the origin, if you restrict to a small sphere, then you won't have a critical point, so the gradient's not 0, so I can divide by this. You get this well-defined map. And Milnor proves that the Milnor number is the degree of this map. And it's known from standard intersection theory that this is the same, and Milnor doesn't ever use this to calculate. But it's known from standard intersections theory that this is the same as you take the ring of convergent power series at the origin, and you mod out by the Jacobian ideal, the ideal of partial derivatives generated by the partial derivatives of f. In the algebraic setting, you could take the polynomial ring, localize at the origin, and mod out by this. You get the same thing. Is that okay? Okay, so it's nice that it's you have this algebraic characterization of it. It makes it very manageable to calculate. You can do it by hand in relatively easy examples. You can do it by computer in tougher ones. But it's a single algebraic number that you really can calculate that tells you about the homotopy type of this fiber. And then there's another reason it's so important is the result of Ley and Ramanujan that, which is from 70 something. I really can't remember, 78, 74, one of those. 1970 something. That if the Milner number is constant in a family, so if you've got a family of these polynomials, these analytic functions, and again, this is still in Cn plus 1, but now this is a T is a parameter in some complex disk. So a one parameter family of analytic functions with isolated critical points. I won't bother writing that because I'm going to write that their Milner numbers are constant, and I wouldn't have any if they didn't have isolated critical points. And mu0 of ft is constant in T. Then the local ambient topological type of the hypersurface defined by f in U at 0 is constant, provided this is if n is unequal to 2. So the Milner number completely controls the local ambient topological type, so how the hypersurface sits inside of affine space, provided that n is unequal to 2. I know you know this. I don't know if you know this. This gap at n equals 2 is caused by the use of the H-cobordism theorem in the proof. And when n is 2, the Milnor fiber is a 4-dimensional manifold, and we can't use the H-cobordism theorem. When n is 3, suddenly you're in a 6-dimensional manifold. That's fine. When n is 1, you're a 2-dimensional manifold with boundary. Well, you use classification of surfaces, then that's not bad. All right. So that's the Milner number. It's relatively calculable. Maybe I should calculate because I'm going to calculate something else after this, and I want it to look similar. I can't even guess how many times Marcus has seen this calculation. I suppose we can calculate something else. So let's do y squared minus x cubed minus x squared, x cubed minus x squared, and y squared minus x cubed, and what's the Milner number of, let's just go crazy and do an x to the alpha plus y to the beta plus z to the gamma. Uh-oh. All right. So, of course, you calculate it this way, by the dimension of this Jacobian algebra. So the partial derivatives, don't tell me, I'll get it. Minus 3x squared minus 2x, 2y. Okay. What happens? Well, the 2 doesn't change the ideal. The ideal generated by this and 2y, same as the ideal generated by this and y. You're taking the ring of convergent power series at the origin in x and y. You completely mod out by the y. So this is, you just set that, the effect of that is it sets y equal to 0. So that's the same as the dimension of, you might as well change these minus signs to plus signs just because. It's the same as this. Anyone? Anyone? What is this?
It's x times a unit.
It is x times a unit. That is x times 3x plus 2. 3x plus 2 is a unit in this ring. It's invertible. 1 over it is a convergent power series at the origin. So this would be the same as the ideal generated by that. Oh, that wipes out the x's. You have the dimension of c over c. Wait, I'll do it in my head. It's 1. All right. So that one's 1. U0 of y squared minus x cubed. This would be the dimension over the complexes cxy. And then you just get minus 3x squared 2y. The 2 doesn't matter. The minus 3 doesn't matter. You wiped out the y's. This would be the same as the dimension over the complexes cx mod x squared. This is the dimension as a complex vector space. You mod out, you take the convergent power series at the origin in a single variable, and you mod out by every power of x squared and everything you can get from multiplying by that. So every power of x squared and higher powers of x. That leaves you with 1 in x, and then a times 1 plus b times x as a complex, as a vector space. This is two-dimensional. Its basis 1 in x. So this is 2. This is kind of your classic Breeze-Korn variety, or polynomial defining a Breeze-Korn variety in 3 variables. Its Milnor number.
Alpha minus 1 times beta minus 1 times
Yep. Yep. Yeah, the partial derivatives, the alpha, the beta, and the gamma that you get as coefficients won't matter. You'll have x to the alpha minus 1 and a beta, y to the beta minus 1 and a z to the gamma minus 1. This is what you end up with. All right, great. The Milnor number is easy to calculate in easy examples. All right. But now, the question, or a big question, is what should replace the Milnor number for a non-isolated hypersurface singularity? And a lot of people have had a lot of different ideas of what you should do. Like you could look at just the Euler characteristic of the Milnor fiber. That would be kind of a weak attempt to replace the Milnor number. It has the advantage of being calculable. One of the things people would like to do would be to give some kind of numbers that enable you to calculate the cohomology of the Milnor fiber, or up to homotopy. Well, let's try that again. To calculate something topological about the Milnor fiber up to homotopy, so, or just calculate the cohomology groups. Yeah. Ideally, it would be something effectively calculable, like the Milnor number. But part of what I want to say today is that it's just the wrong question to ask, to ask to be able to calculate some numbers that would tell you even the cohomology of the Milnor fiber in this case. It's the wrong data. I'm taking the mathematician's way out. I'm saying, yeah, we don't know how to do it, but we never should have asked that question in the first place as a general hope. So let me calculate something and spend the rest of the time telling you what I've calculated. So Marcus, you've seen this example. Robbie just saw it last week or the week before, can't remember. So I'm going to take this polynomial, which for a long time I've referred to as the FM cone. And its critical locus, actually let me pick an ordering on the coordinates. So I'm going to order my coordinates. U, V, W, X, and Y. Perversely, even though there's no Z sitting here, I usually call my coordinate vector Z, so I guess I'll call this Z. I guess at least it won't get confused with any of the coordinate names, of the individual coordinate names. The critical locus of this is very non-isolated. It's not an isolated point at the origin, the critical locus. The partial with respect to x minus 3x squared plus 2 u squared plus v squared plus w squared x. Actually, usually I would put a minus sign in here. It doesn't change anything except usually it would change your ability to draw things over the real numbers, but we're already in 5-dimensional space. We're not going to draw that even over the real. Still, I usually put in that minus sign, so let me go ahead and make that minus. Good reason. There's the partial with respect to x, the partial with respect to y, and then the partials with respect to u, v, and w. So minus 2u x squared minus 2v x squared minus 2w x squared. So what does this reduce to? Well, if you look at these three, so if x is 0, all of these three would be 0, this one would be 0, and you'd need y to be 0. So you at least get where x is 0 and y is 0. What else could you get? All right, if x is not 0, then you need u, v, and w to be 0, these three to be 0. Once u, v, and w are 0, this part's 0, and you need minus 3x squared to be 0, so x has to be 0 again. So this is it. This critical locus is v of x, y. But that means it's actually, with my coordinates ordered like this, means these first three coordinates can be anything. So it means it's c cubed cross 0. So it's a 3-dimensional critical locus. I typically draw just the critical locus in this example. It's just 3 space. U, v, and w. But this is just kind of an illustration of the critical locus. And it looks like something interesting is happening maybe where u squared plus v squared plus w squared equals 0. Now I should, if I wanted to draw this over the reals, there should be some minus signs. One of these should be negative, but strangely I never put those in. But it looks like there might be something going on along a cone where u squared plus v squared plus w squared is 0. Okay, but I actually want to calculate some things. So let's calculate. I am going to spend the rest of the time, like I said, the last 30 minutes, explaining what I've calculated and why I think it's the right thing to be calculating. But if you know stuff I've already done, and I know you do, you'll recognize that what I'm about to calculate are lay cycles, but then I'm going to subtract away a part of them. Ha! Ha! Yeah. So I'm going to calculate lay cycles. And I don't have time to define them in general. It's not really the point of this talk, although if you want to calculate what is the point of this talk, this is how I suggest you do it. So with that choice of coordinates fixed, I'm not going to indicate the coordinates in what I write, although generally you would need to. I'm going to look at the four-dimensional relative polar variety, or relative polar cycle. I'm starting one dimension higher than the dimension of the critical locus. And what this means is this is just defined to be the cycle, so not a cycle class, not up to rational equivalence, just the cycle. The cycle defined by where the last partial derivative vanishes, last with respect to the ordering I picked on my coordinates. So this, and this is v of 2y, of course it's just v of y. The gamma means I only keep the portions that are not contained in the critical locus. This is four-dimensional. The critical locus is three-dimensional. There's no way any component of this is contained inside the critical locus. That's why you start there. And then you take gamma 4 and you intersect with the vanishing of the next partial derivative, which in our ordering is the x partial derivative. So it is minus 3x squared minus 2x times u squared plus v squared plus w squared. Now, intersection numbers, well, they have lots of properties, but one of them is that because this, you can factor an x out of here, this splits up as this cycle that we're intersecting with splits up as a v of x cycle plus, and I'm going to get rid of the minus signs, 3x plus 2 u squared plus v squared plus w squared. Tell me if I mess anything up. And now you do this intersection. And what you get, except I want to change the order that it's written in, just because I always write it this way, is the cycle defined by there's this and this. This is where I'm changing the order. So the cycle defined by the scheme this plus this part, plus v of xy. Right. This part is contained inside the critical locus. In fact, as a set, it is the critical locus. But I mean this as a cycle. I mean this as 1 times this. So by cycle, I just mean an irreducible variety with a multiplicity attached to it, a positive, a non-negative multiplicity. This is what I usually refer to as the three-dimensional lay cycle. So, and this is now the three-dimensional relative polar cycle. And you keep going. So you do this to calculate gamma 3 and lambda 3, and you keep going until you get down to lambda 0. And then I'm going to do something that I don't usually do. So gamma 3 well, let me write F over again since it's vanished from the board. And then gamma 3 intersected with the next partial, where the next partial derivative vanishes. The next one is the one with respect to the ordering on my coordinates. U, V, W, X, Y. So we've done that one, we've done that one. Now we're at this one. And so what you get is the partial with respect to W minus 2WX squared. All right? The 2 doesn't matter in the cycle. This is a product of things, so it splits up as a sum. So you get V of the gamma 3 is 3x plus 2 times u squared plus v squared plus w squared. And then there's intersected with v of w plus v of x squared, but that's 2 times the cycle v of x. So this is plus 2 v of x. So what you get is you get a v of, what happened to my y? I left it out. There should have been a comma y right there, right from there. All right, so you get a v of, there's a w, there's a y, and then there's 3x plus 2 u squared plus v squared plus w squared, but w is 0, so just that. And then plus this intersected with this. So now x is 0 and y is 0, and we don't need that. So we get v of x, y, and then we don't need the 2. U squared plus v squared plus w squared. And this is gamma 2. This is lambda 2, two-dimensional phase cycle. Gamma 2 intersected with where the next partial derivative is 0. It's the partial of f.
Do you want to count that bicycle twice?
Oh yeah, sorry, thank you. Yes, that's very good. That 2 right there. Thank you. Actually, no, that's gonna. I was gonna say that part's gonna cancel out, but not at this stage. It's not. That 2 right there is not going to. All right, then you intersect this part with where the next partial derivative is 0. The next one is one with respect to v. So you get a v of w, y, 3x plus 2 u squared plus v squared. Intersected with where the partial with respect to v is 0, so that's minus 2vx squared. Again, this splits off as where v is 0 and then a 2 times v of x. Where v is 0, and you intersect with this, I'm speeding up, you get wvy, and where v is 0, you get a 3x plus 2u squared, plus, and then where x is 0, so you get a 2 times v of, there's a w, x, y, and then u squared plus v squared. This is gamma 1. This is lambda 1, the part that's contained inside the critical locus. Right? This part's contained inside the critical locus. That part's not. And then I should be recording these. So I just want to record that gamma 3 is v of xy before I erase it, although that would have been easy to remember. And then you take gamma 1f and intersect where the final partial derivative is 0. So this is v of w, v, y, 3x plus 2u squared, intersected with, yes, I didn't get this out of my way. Intersected with this last partial derivative, minus 2ux squared. And then what do you get? All right, when u is 0, you get v of all the variables. So you get v of, well, that's just the origin, one time. But then you add to that 2 times what happens when x is 0. 2 times what happens when x is 0. When x is 0, you'll set that one equal to 0, and you'll get a u squared. So you get 2 times 2. That's 4 zeros. So you end up with 5 times the origin. So this is what we find. We get this lambda 3 of f is v of xy. Lambda 2 of f is this 2 times v of xy comma u squared plus v squared plus w squared. Lambda 1 of f is this 2 times v of wxy, u squared plus v squared. Wxy. And lambda 0 is 5 times the origin. Great. These are the Lay cycles. I've known how to calculate these for almost 20 years now. And their intersection multiplicities with the defining coordinates were my idea of what to replace the Milnor number with. They are, in a sense, good at that. They're the ranks of some modules in the differential complex, and the homology of that complex is the homology of the Milnor fiber, so there's some Morse inequalities satisfied. Their constancy of the numbers, so I'm talking about intersection numbers of these with the coordinates that define, with the defining coordinates. The constancy of the Lay numbers in a family give you constancy of the Milnor vibrations up to various things. It's been proved by Bobadilla that the constancy of the Lay numbers does not imply the constancy of the local ambient topological type. Produced a counterexample, but he did prove that it implies the constancy for families of one-dimensional hypersurface singularities. So that's one dimension better. But I don't think the Lay numbers are the right replacement for the Milnor number. They depend on the choice of coordinates, which is not nice. Generically, they don't. For a generic choice of coordinates, all the Lay numbers would remain the same. But what this example shows is that they're actually not, in a sense, they're not even there. Because there's really no difference. This problem is completely symmetric in u, v, and w, completely. There's no difference between those 3 coordinates. So yeah, you ought to have this three-dimensional critical locus that's C3, and you have this cone of things where u squared plus v squared plus w squared equals 0. That's really something that's there where something changes, where something topological changes, the Milnor fiber changes. But this lambda 1, nothing happens here. There shouldn't be any one-dimensional activity. There is nothing, those are that's a pair of lines. The u squared plus v squared equaling 0 would be a pair of lines, and then they occur with multiplicity 2, but it's a pair of lines. Well, there's nothing happening along this pair of lines. That's there because of the coordinate choice. And it doesn't really belong there, or they don't really belong there. And so what should you do? What you should do is every time you calculate one of these higher dimensional lay cycles, you need to do something. So you need to calculate its absolute polar varieties, the absolute polar varieties of lay and Tessier. Take the absolute polar varieties of the bigger lay cycles and subtract them from the smaller ones to see what is actually there, see what's really there. So what am I babbling about? This is smooth. It has no polar varieties of smaller dimension than this. You can take the three-dimensional absolute polar variety of this, and you'll just get this. But what I'm claiming is this. This is singular. This is this cone. And what we need to do is take the lay cycles and subtract the absolute polar varieties you get from this from the lower dimensional lay cycles to end up with something that's intrinsic. It doesn't have anything to do with the choice of coordinates. Then this won't have you don't have zero-dimensional absolute polar varieties, so you won't have anything other than the one-dimensional one here. You won't have a zero-dimensional one here, and you don't have to worry about it for here. What I'm saying is, in this example, what I want to do is calculate. I want to subtract absolute polar varieties, but as cycles. So subtract absolute polar cycles. These are the polar cycles, or polar varieties in the cycle form of lay and Tessier. Subtract absolute polar cycles of smaller dimension. And I'll make this clear with this one example. From the lay cycles of the same dimension. So what am I talking about? The absolute polar cycles. You make a choice of coordinates. Lay and Tessier talk about picking, making a choice of linear subspaces. So they talk about picking a flag, but it's the same as making a coordinate choice. So I'm still taking my coordinates in this order because I want to subtract the things that were caused by making this coordinate choice. What I'm saying is I need to look at gamma 1. This is not relative. It's the absolute polar cycle. It's not something you do to the function f. It's something you do to a set. I want the absolute polar cycle of, 2 v of x, y, u squared plus v squared plus double u squared. What does this mean? Well, the 2 just goes along for the ride. It's a cycle calculation, so it's 2 times and 1 of this reduced thing. And what this means is this is a 2-dimensional thing. You project onto the coordinate space that's 2-dimensional starting from the left end. So you project with u and v. So this is nothing other than the critical locus. So I guess I'll continue to write sigma for critical locus, even of map of, well, no, I won't. It's the critical locus of the map uv restricted to v of x, y, u squared plus v squared plus w squared. So this is a map from here to C2. It's a two-dimensional thing. You're mapping to C2. We should expect a one-dimensional critical locus, and that is what we'll find. So how do you find the critical locus of a map like this restricted to this set? Well, first of all, x and y aren't doing anything. You might as well just pretend x and y are 0 and just, well, they are 0, but just ignore them. Look at the critical locus of the map uv restricted to u squared plus v squared plus w squared. How do you do something like that? Well, it's you take the partial derivatives of this. Well, you make so you make a matrix. You take the gradient of this, and then you take the gradient of each of these things. So you get a 1, 0, 0, and a 0, 1, 0. And then its square, you take its determinant. You see where it's equal to 0, and that'll be the critical locus. The determinant of this should just be 2w. It's this times this. Yes, it's 2w. Yes, yes, it's 2w. And so what does that mean? This critical locus, this critical locus is with the x and y in it. It's v of x, y, w, and u squared plus v squared. So this thing is nothing other than v of x, y, w, u squared plus v squared. And you've got 2 times that. And what I'm saying is you need to subtract that. So that's a one-dimensional object. You need to subtract that from the one-dimensional Lay cycle. Well, that is the one-dimensional Lay cycle. And so you end up with nothing here. And what I'm saying is the cycle that we ought to care about is something I would call a Milnor cycle. So we're left with and I've never defined a Milnor cycle before, but I think this is the right thing to look at. And so you just take what's left, weighted with their multiplicities. So you get a 5, maybe I'll write them in ascending dimensional order. You get a 5 times the origin, plus this is gone, plus a 2 times v of, so now I'll put square brackets around cycles just to make it more clear that they're cycles. And then plus a v of xy. What's so nice about this? Well, first of all, it's intrinsic. It doesn't depend on the coordinate choice. Well, it does and it doesn't. I'll explain this too, but you had to know that the coordinates were generic enough in the first place, which is one of the major problems with effectively calculating things in this whole game. It's how do you know your coordinates? You can do calculations, but then how do you know your coordinates were generic enough so that what you've calculated is what you were trying to calculate? And what I like is when you can take what you end up with and then verify something and go, yep, that was generic enough. What I don't like is actually having to vary your coordinates generically and see that nothing moved. That's actually very painful. So this is what I'd like to call the Milnor cycle. It's independent of the coordinates. It's, in that respect, it's intrinsic. You could recover the Lay cycles from it just by throwing in absolute polar varieties of things that are here. So you could do that. But really, what is this calculating that I think is what you should care about? So what is it that this is calculating? I claim that what we just calculated, we essentially calculated the characteristic cycle, and there are different notations for this. I'm going to write CHAR. Some people would just write a CC. And there are different conventions on plus or minus signs. So other people would put in a plus or a minus. But I'm just going to say we calculated the characteristic cycle of the vanishing cycles of the constant sheaf, and I'm going to put in the shifts that would make things perverse sheaves, but you don't have to do that, especially since I'm not going to worry about the plus or minus signs. But we calculated the characteristic cycle. This is the characteristic cycle. It's something you can calculate for a complex of sheaves. And this is the complex. It's a complex of sheaves, but people frequently leave off complex of, and they just say it's the sheaf complex of sheaves of vanishing cycle. This is what keeps track of Milnor Fiber data on the sheaf level. All right, I do want to say some more things about this. What do I mean we effectively calculated it? What we've got is this Milnor cycle, and it's some sum. It's some sum of some multiplicities times some varieties, some cycles. So I'll just write the alphas. This is clearly not a characteristic cycle. If you have any idea what a characteristic cycle is, why not? Why is it most obviously not a characteristic cycle of anything? It doesn't even sit in the right place. Characteristic cycles sit inside the cotangent bundle, and they don't lie inside the original space. So what do I mean? This is the essentially part. What I mean is the characteristic cycle is actually that, but you take the conormal varieties to each of those. So I really mean the characteristic cycle of the sheaf of vanishing cycles of that. I really mean that what we just calculated tells us this is 5 times the conormal. We don't need to close that one, it's already closed. Plus 2 times the conormal of, well, really you have to take the regular part of, so you would remove the origin because it's not a smooth point, and then you close it, plus 1 times. And this one, again, is already closed. It has no singular points. So what I mean is we calculated it. You just take the conormal varieties to each of those varieties I wrote over here, the conormal varieties to the smooth part of each of the things I wrote over here. The reason I think most people would prefer to write this is you kind of want something that generalizes the Milnor number. You think of the Milnor number as being attached to the isolated critical point. So you want something that lies inside your original critical locus, like this does. And yeah, you could of course say, I want to look at the characteristic cycle. And maybe you do, because part of what the characteristic cycle does for you is it tells you directions of well, that are normal to your variety. Really, they're conormal because they're covectors, but you picture them as being normal to your variety. It tells you more about the geometry. But of course, in theory, if you know what I've called the Milnor cycle, you know these because you just calculate the conormals of what you've been given. So I think you know all I want to say about, I just quickly want to say what some properties of the sheaf of vanishing cycles. I don't want to find that either. You guys probably know this already, but for people who watch this later, I should spend about 10 minutes giving some basic properties of this and then what the characteristic cycle of a complex of sheaves means. So what is the sheaf of vanishing cycles? So I get tired of writing all of that over and over again, so let me put some fancy F on the board just so people have trouble copying it. So let me call this complex of sheaves F. All right, what's the big deal about, or what is the sheaf of vanishing cycle? So let me just say this quickly in an easy case. Suppose you've got a function with a one-dimensional critical locus. So maybe the critical locus itself looks like this. What is it? What's the sheaf of vanishing cycles? It's supposed to keep track of Milnor data, but at each of these points in the critical locus. Actually, you could ask for it at every point in the hypersurface defined by F, but it's only non-trivial at points in the critical locus, so I won't bother saying that. What you'd like is at each point in the critical locus, you want the stalk of this, actually maybe called it F dot, but maybe I won't use that right now. We want the stalk of the vanishing cycles if you take the kth cohomology of this, the stalk at a point x inside the critical locus. What we want this to be is, well, I've got so many shifts in here, it's a little hard to see. I'm used to these shifts that make things perverse. So what we want this to be is, put it up here, but we want the reduced cohomology. Let me just ignore which degree we're in so that the shifts won't look so weird to you. We want this to give us the reduced cohomology of the Milner fiber of F at X. It is a sheaf theoretic construction that does this, and the sheaf, the complex of sheaves, just keeps track of how local data patches together. So it's a complex of sheaves that kind of gives you the Milner data on the cohomology level at each point in the critical locus. It's actually a complex of sheaves defined on V of F, but its support, the only places where it's non-trivial, is the critical locus. So what do we want out of what does this do for us? It's easiest to talk about in the one-dimensional case. So there is no Milner number here. But what is there? Well, at a generic point, you move out here and you take a normal slice. You take a generic slice to this. Normal meaning it's of complementary codimension, and you take a manifold that slices this stratum in a single point, and then you have an isolated singular point, and it'll have a Milner number. And so out here, that will completely describe the cohomology of the vanishing cycles, the Milner number of this transverse slice. What's interesting is what happens at special points. So in a zero-dimensional set inside of here, there would be places where, yeah, something special happens. And what we want, what I was saying is, when I said that it's the wrong question to ask to calculate the cohomology of the Milner fiber, this is what I mean. It's the Milner fiber itself is a perturbation of the hypersurface. It's a Morse theoretic thing. Right? It's what happens, what did I attach as I move from this smooth hypersurface, the Milner fiber, through this critical point. what did I attach to fill in all the cohomology? Because you know as you pass through there, you end up with something contractible. So it's another Morse thing. What you should ask for here is not the cohomology of the Milnor fiber there, but how the cohomology of the Milnor fiber changes as you move from this slice and pass through here. So if you take a slice down here, you have three Milnor fibers in my picture. You'd have three Milnor fibers. That would have some cohomology. As you pass through here, the question is what gets attached? You know, how did the cohomology change as you move through here? And this is an iterated vanishing cycle construction. It's you're really taking kind of a phi of, or not kind of, you're exactly taking a phi with respect to some linear form of the complex of vanishing cycles and asking what vanishes. And you can iterate this and take a slice and then take vanishing cycles, and take a slice and then take vanishing cycles. And this kind of iteration, this is what gives you, for instance, the dimension of this. Only the 0th dimensional cohomology would be non-zero here. And this dimension would in fact be the 0-dimensional Ley number. But the Ley numbers depend on the coordinate choice. And that's because you make one coordinate choice and you use it everywhere. And when you have something like a cone, what happens is down here you make a coordinate choice and there's a critical locus of two lines along here, as we saw. And yeah, that comes from our coordinate choice. But if you moved out to one of these points and then picked a new generic choice of coordinates out there, this pair of lines would disappear. You wouldn't see this line at all, as you shouldn't. And that's the difference between the characteristic cycle and the Ley cycles. The characteristic cycle actually moves to generic points on strata and then takes a normal slice there and then takes a linear form inside that normal slice. But you get to change the linear form and the normal slice at each point. So typically the generic calculation is tougher, but the Ley cycle calculation was very algorithmic, and then you subtract the relative polar varieties. Why does that work? And I'll just say this and I'll stop. Actually,
Absolute polar varieties.
did I say relative?
Yeah.
Yeah, absolute polar varieties. I proved quite a while ago now, that in fact lambda k of f with respect to z is the sum of m alphas times the gamma, the absolute polar varieties of the same dimension of S alpha, where, ooh, this is bad. I should put a complex of sheaves here. And where characteristic cycle, so in the case that we're talking about, this complex of sheaves, so I'm doing this in the general setting, would be the one I wrote over there. So if you put the vanishing cycles here, this is the same as the Ley cycles of F. But you can do this for any complex of sheaves. And what's M alpha and S alpha? This is where the characteristic cycle of F dot is the sum over alpha of M alpha times relative conormals. So if you know the characteristic cycle, you can calculate the Ley cycles like this. But what I'm advocating now is the calculation of the Ley cycles is algorithmic. And then if you use this formula, you just subtract off the parts. You subtract off the parts that are coming from lower dimensional k's. What do I mean lower dimensional? I mean when k is less than the dimension of S alpha, because when k is just the dimension of S alpha, this is just S alpha closure. Right? So this. So the calculation, in the calculation that I did, I just subtracted off that contribution, and it leaves you with just the M alphas times the closures of the S alphas in the characteristic cycle. And this is what I think is the right thing to look at. All right, I should stop. I have gone over time, but I'm happy to take questions. We have lots of space on our cards. I'm happy to have no questions.
So is it true that for every Milnor cycle there's a unique characteristic cycle or a complex of sheaves of vanishing cycles?
There'd certainly be a unique corresponding characteristic cycle. You just take these coefficients times the conormals to these. I didn't say what conormal variety is. I don't know if you know. It's the set of cotangent vectors that vanishes on the smooth part. Together with the points in the smooth part. So yeah, but certainly the Milnor cycle, it's even for Milnor numbers, that's not true, right? So if just because two hypersurfaces have the same Milnor number, in no way, shape, or form does that mean they're ambiently homeomorphic. In fact, I think that came up during a talk of yours one time. Quick, what's an example? Oh yeah, I didn't make the conjecture. I did. What I do think is true. That's like Lay and Ramanujan, or what I suspect is true. I'm not sure I want to make a conjecture. Is that if you have a family and the Milnor cycles are homeomorphic in the family in such a way that the multiplicities are the same, and there's a homeomorphism of critical locus at each t, it takes the varieties that are appearing there to each other. And I think you probably need that homeomorphism preserves degree, that each of these pieces has the corresponding pieces under the homeomorphism need to have I said degree, I mean multiplicity, have to have the same intersection multiplicity, maybe at every point, but it might be enough to be at the origin if you're looking at the ambient type at the origin, right? Because you might have heard the Zariski multiplicity conjecture about hypersurfaces being ambiently homeomorphic, having to have the same multiplicity. It's once you're beyond hypersurface, there's no question that just fails, because any curve that's in more than C2, so any curve that's in like C3, any two of those are locally ambiently diffeomorphic because they're unknotted. There's enough dimensions you can just unknot them. So that means that this curve and this curve are ambiently homeomorphic, locally ambiently homeomorphic inside C3. Well, it's a bit much to think that that would imply constancy of the ambient topological type in a family. I mean, maybe all you need is homeomorphism, but I wouldn't be surprised if you also needed to require that you don't have these things being mapped to each other. That you need the multiplicity here to be the same as the multiplicity there, and the multiplicity here to be the same as the multiplicity here. But I suspect something along these lines is true, and of course for families of isolated critical points, you get the homeomorphism free because it's, oh, this point's homeomorphic to this point. Yeah, really? But no, Milnor cycles definitely doesn't characterize the function in any significant way. Is this related to quantum field theory, that question?
Still trying to
However, it may be, and we'd have to think about it, that if it came from a quasi, well, actually that's, no, even that's not believable. I wouldn't even believe that if you knew that this came from a quasi-homogeneous polynomial, what would that characterize the quasi-homogeneous polynomial up to? It might tell you the weights of the variables. No, that's false. That's false even for Milner number.
Well, you can have well-defined weights and one of them be 0 and still have a one-dimensional critical locus.
But what I'm saying is that even if you knew that the function worked, even if f is polynomial and it's weighted homogeneous and you knew this, I don't think it characterizes it up to much of anything. I was wondering out loud if maybe it gives you the weights, but it doesn't. Right? Because even for isolated singularities, knowing the Milner number doesn't tell you the individual weights.
Right.
So I don't think knowing this would tell you f in any reasonable way for any class of f's. Can't think of. It's too weak. Which is what makes theorems like requiring it to be constant implies the constancy of the topological type in a family, because it is weak. In no way do you expect it to characterize f, and yet somehow, once f is in a family and this weak data doesn't change, like Milner number for an isolated critical point, this weak data doesn't change. Once you're in a family, it's enough. It's bizarre, really, when you think about it. It is extremely weak data.
So in the Milner case, and by that I mean when the critical locus is
Point.
trivial, right? And you have a weighted homogeneous polynomial, and you add sums, squares, if you will, then you don't really change anything. It's just a suspension, and you have some invariance of the Milner number.
That's true. I mean, it's.
Is there something that is similar to that?
Yeah. This when you suspend, when you add a disjoint variable squared. Yeah, there's the general Sebastiani theorem that tells you that effectively it only changes this up to a shift in the cohomology. So the cycle wouldn't change except with a, actually it wouldn't change, period.
So you have the same reduced cohomology and the same weight.
Well, this would be, the cohomology would be shifted, but
Yeah.
aside from that, it would be the same. The Milnor cycle, depending on exactly how you define it with pluses or minuses, I would like for it to be a positive cycle. If you define it that way, it's not going to change at all. Because all the shift here would do would put things in a different degree. But it's like saying that, for instance, if I had a Milnor number, if I had an isolated critical point, Milnor cycle would just be Milnor number times the origin, telling you that it's there that many times. If you shift that, yeah, you'd still just get same Milnor number times origin. The fact that that Milnor number is measuring something in a different degree isn't encoded here in this cycle. So, yeah, this wouldn't change at all, regardless of whether the critical locus is a point or not. So in that respect, I think you've told me quantum field theories you care about that when you suspend, effectively nothing changes. Yeah, this doesn't change.
That shifts.
Yeah. Well, here there's not even a shift. The shift that you're talking about actually looks more like really looking at cohomology, because that also shifts.
So what happens when you do, I mean, so this is invariant under generic H support.
No, this is completely invariant. This would never move.
Oh, wow.
This is the characteristic cycle. It has nothing to do with the selection of
Yeah,
coordinates.
Yeah.
The point is that the calculation of it in this algorithm, ideally, in this example's easy enough that I know this is right. But ideally, you would do the algorithm that I was following for calculating lay cycles, and then you would calculate polar varieties and subtract them, and know that what you end up with is the right thing. It's what you get from the characteristic cycle. Unfortunately, to know that that calculation is coming, to know that what you end up with comes from the characteristic cycle, you really need to know ahead of time that some intersections up in the cotangent space are proper. But that means, what intersections? Well, the intersections with the conormal varieties of the strata that actually appear in the characteristic cycle, and some particular copies of projective space, the ones defined by the coordinates. Now, I've tried for a long time, and I think I might be about to fix it. I'd like to know that you can do this calculation and check something in this calculation itself and verify that things were generic enough. That's kind of the dream, or that's ideally what you'd be able to do. I don't know how to do that yet, but I feel like I'm about to do it. It is kind of a weird thing. I know from lots of formulas for lay cycles that they have all these properties about what happens when you slice, and the alternating sum gives you the reduced Euler characteristic of the Milnor fiber, as long as as long as you can carry out the calculation I carried out. As long as things are generic enough for those things to come out the right dimension and the intersections come out the right dimension, generic enough, the alternating sum's the Euler characteristic. But I don't know that that's generic enough to make sure that everything that this formula is true. This requires more genericity, and it is kind of the flaw in calculating this algorithmically, which is what I want to be able to do. 'Cause I hate, I hate the aspect of algebraic geometry where you really have to put in kind of generic coordinates and then figure out what. So you take generic linear form, so you put coefficients in front of the coordinates and you add them up, and then you find the conditions on those coefficients that make bad things happen. And I hate that. It's awful. I like to calculate it. Should we stop?
Yes.
More questions?
That's great, thank you.
You're welcome. Thank you.